Okay, so we'll start. Okay, so we'll start now. So I just made a small Notion note for this for the fetch code execution cycle. I'll share this notepad with you after the session. So okay, I hope you know all the basics. What is PC, MAR, MPR, etc. So I'm just directly going into these steps one by one. So the first step is fetch. So in this step, uh, the first, okay, 1 6, that's simple. Yeah, the pipelining is coming up. Kanishka will take it after she joins the meeting. She'll just join in a bit. Okay, so let's start with the fetch part. So as you know, the program counter stores the memory address of the next instruction that has to be executed. And okay, I'll just brush up with all these concepts once again. So this is program counter, and MAR holds the address of the current location in memory being accessed, and the MDR is the same but for data or instruction. And CIR or as in, like in class you would have read about it, referred as just IR. So IR just holds the instruction that is currently being decoded and executed. Uh, the point to note is that IR contains the instruction and but PC contains the memory address. So PC contains the address of the next instruction, and IR contains the instruction itself that is being executed. And the control unit is the boss. So it is the orchestration, like it maintains the orchestration. So like it controls all the units, the PC, MAR, etc. So it is the unit that controls everything else, and ALU is the unit that is responsible for the calculations. So the first step, the CPU looks at the PC to see which memory address holds the next instruction. So it will start. The fetch cycle starts from seeing what the next instruction is. For that, it need the memory address of the next instruction, which is stored at the PC. This address, the address of the next instruction, is copied into the MAR. So that means that uh, now we are going to execute that particular instruction, right? So this instruction's address is copied in MAR. Then after the address is copied, the control unit, that is the CU, sends a read signal uh, along the control bus to the memory. So we have two parts, the memory and the CPU, right? As in, yeah, the CPU. The control, I mean, by CPU, I mean control unit. So the control unit sends a read signal to the memory through a control bus, and at the same time, it also sends the address in the address bus. So the memory gets two inputs. One is the signal. Here it is read signal, and the other input is the address. So the memory gets these two inputs from the control unit, and it will know that that particular address has to be read. Then, so if it has to be read, that like then the memory has to return that particular the values that resides in that address, right? So that's what happens in the next step. The RAM, it is the it is the responsibility of the memory. Here it is RAM. So the RAM locates the data at that specific address that the control unit provided and sends the instruction back to the CPU via the data bus. So here it is specified as instruction, but generally, in general, the data is sent back to the CPU via the data bus. And after this, the this instruction or this data arrives and is stored in the MDR. So far, these are the steps that we have completed. So the next step is this instruction, that is this data, is copied from the MDR to the current instruction register, that is IR. So this IR contains the current instruction that is being performed, and then the PC is incremented. So this is end to end the entire life cycle of the fetch cycle. So the next step is decode. In decode, this control unit looks at the instruction in the IR. So now that the PC helped the control unit and control unit kept the current instruction in the IR, the next step in this decode step, the control unit first looks at the instruction in the IR, and then this instruction is split into two parts. One part, the first part is opcode and operand. Opcode is the basically operation code. It tells what operation has to be done, and the example add, load, store, etc. And in the operand, uh, yeah. So the operand has the number that the data in which it has to act upon, and this data is then sent to the ALU, and then ALU computes the computes the computation, makes the computation whatever is required. Then the third step is execute. So yeah, as said earlier, execute steps are of three types. One is mathematical, that is adding, subtraction, etc. Data movement is basically when you load a data or move some data from one register to another, or one, like you are setting a constant value to a particular register. In such cases, it is called data movement. And control flow is when in the codes that you have written, you would have written jump, etc., jump and some similar commands, right? So jumping will happen in for loops or if loops. I mean, if conditions. So this kind of instruction is called a control flow instruction. Yeah, and this has a practical example also, which you can refer in your own time. Give me just a second. So yeah, that is fetch, decode, execute cycle. If you know this workflow entirely thoroughly, it is very easy to get marks in conceptual questions related to this. Do you have any doubts in this so far? Okay, so now Kanishka will take over and teach you pipelining.
clothes, we need to load them, then rinse them, then wash them. Finally, you need to dry them. So these are four different processes to wash a single piece of clothing. Okay. So imagine there are a lot of people, for example, in hostels or any place. Okay, and some, yeah, and even at your home. Okay, there are so many people, and each of them have different sets of clothing. Each one, they have to do all these processes, and each process takes about half an hour. So in the timeline, if we see, loading takes half an hour, then rinsing takes half an hour, and again, if you see, washing also takes half an hour, and drying also takes half an hour. So approximately it takes 2 hours. So for each person to do this process separately, it'll take about 2 into 4, which is 8 hours. So here comes the concept of pipelining. So in pipelining, what we do is we do not increase the speed of any of these processes. The time each process takes always remains the same, but you just increase the throughput. Throughput in this case means, when see, in this example, it means that when other process is doing, so for example, say one person is loading the clothes. When the only one set of these yeah, electronics are available, like these processes, only one set are available, think that way. And then one person, imagine there are 4 people, A, B, C, D, as given in this example. So when A is loading the clothes, all others have to wait, because they don't have any other thing which is available right now. So when A is loading, everyone has to wait. But when A has moved to rinsing, the loading which A has done is free right now. So B can load when A is moved to rinsing. So similarly, when we do all these processes concurrently, like you should not confuse this between parallelly working and pipelining. Parallel is when different sets are available, like you have a different washing machine for loading, storing, etc. When you have many multiple sets, and all people do it simultaneously, so that will take much lesser time, because same time people can do their job at the same time. That is different. But here we do it concurrently, like when A is washing, B has to load the clothes. Then when A is moved to washing, then B can move to then B can rinse the clothes. Then when A has dried the clothes, then B will dry the clothes. So similarly, C and D also will follow the same process. This is basically the idea of pipelining. This will differ when each task takes only half an hour. But if time differs, even then it'll definitely take less time than what it takes when it is done separately. So basically, that's all. Yeah. So it's pipelining has been of great help in modern processors. As said, it does not increase the speed, but it just executes simultaneously and increases the throughput. So essentially, essentially throughput means the number of instructions that can be executed at a given period of time. And what else do you? Yeah. So as we have different processes in the washing thing of as such, in computers you have four stages, like you already know. First you have to fetch the instruction, then decode the instruction, then execute the operation, and write back the result. This is a cycle you've already learned. The same thing applies to pipeline. And then these are few things you need to know. So the pipeline cycle time is generally the maximum delay. The delay, in the sense here, it is yeah, as I said, in this washing machine process, every process takes only half an hour. But in actual computers, you need not you cannot expect the same, right? So every time you need to decode some instructions. When you decode, it may take more time than the others. Sometimes like you already know about cache and all that. So when there's a cache miss, it has to go to the main memory. All this takes different amounts of time. We can't really predict that. So for when that happens, that is where this delay occurs. Then when so that is this delay. And non-pipeline execution time is just when there is no pipeline, you just add up all the time. That is what is given here. The ratio, speed up ratio is nothing but the same process when done without the pipeline, and how much it has improved when pipeline is used. This is what is given by speed up ratio. And pipeline for n task is the pipeline for the first task, how much time it takes, plus plus the delay in these tasks from the second and third and fourth task. This is pipeline time for n tasks. And sequential time is just you for the first task, you find the amount of time and multiply it into the number of times number of people are there. Like for example, here ABCD means the first washing takes, example, it takes 2 hours, and here 4 people are there, so it will take 8 hours. That is just sequential time. And throughput, as I said, it's the number of instructions, so it is calculated by n and the total time taken for each instruction. Do you, should I cover the hazards part also, or is this fine? Okay, fine. Yeah. So hazards is when hazards are situations that prevent starting the next instruction. That each instruction has to go follow a certain process. But when these hazards occur, they are unable to do so. So when these occur in 3 different conditions, that is three different types. Those are data hazards, structural hazards, and control hazards. So what is data hazard? Data hazard is basically when you need to wait for the previous instruction to complete its data data read or write. So example, you have 2 registers. For example, you take the example of the basic addition. Okay, so in addition, you for in the first sentence you've given, first line of code you've given si is si plus 1. Si is some variable, or here in this reference you take it as a register also. In each time you have to increment the register. So when this register has been used in the following instruction, it has to wait for the previous increment operation. When this mismatch occurs, the SI sometimes in the next instruction, when the same updated SI, it doesn't get updated sometimes, and this is when data hazard is caused. Like in the previous instruction, you have updated SI to some other register SI to some other value, but in the next instruction, if you have used SI, sometimes it doesn't get updated. That's when this data hazard occurs. So then structure hazards. Structure hazards is when a required resource is busy. That is, if you need some hardware resource like the secondary storage, like the bus or something, when that is not available and it's occupied by some other instruction, this is when structure hazards occur. So whatever resource you need will not be acquired by you because it is busy with some other instruction. This is when structure hazard occurs. Next is control hazards. Control hazards occur when you use statements like jump, branch in your code, and it depends on those instructions. Like branch means it has to branch to the other wherever you've given, it has to branch there. For in the same case, jump also, it has to go to the, if you're given some subroutine or something, it has to go to that. So it depends on that. That's when control hazard occurs. So data hazards are typically of three types. Those are read after write, write after read, and write after write. These are clearly explained by by seeing them itself you can understand. Basically, when a raw hazard occurs when the instruction depends on the previous instruction, that is after when write is done after read. This is when raw hazard occurs. And the war hazard occurs when the previous instruction is read and the value is overwritten by the next instruction, like the example I gave you for data hazard. Yeah. And the write after write is the when the value is written by an instruction written by an instruction before the previous value. Like you have simultaneous we'll see examples down, but you have simultaneous instructions which writes onto the same register. That's when the write after write hazard occurs. So first we'll see raw hazard. So here raw hazard, you see first you're adding R6 and the values of R6 and R5 in R3. So the results are to be written in R3. Then you're subtracting R3 and R5 in R4. So here itself you have the possibility of data hazard or the raw hazard, typical then the subcategory of raw hazard, because first you have to wait for the value of R3 to get updated by the sum of R5 and R6, and then it has to subtract itself from R5 and then store it into R4. So here we can see there's a possibility of a data hazard to occur here. So next we'll see the write after read hazard. Here see, here you're adding the contents of R1 and R0 in R2, and then you're subtracting. So here simultaneously we're using the R0. So sometimes it must so here we are using R0 as a value to as an operand. Like here R0 is an operand, and here we are using it to store the value of R3 and R4. So here data mismatch might occur and it might cause write after read hazard. So here in both cases you're simultaneously adding and subtracting here. So R1 and R2 are added and stored in R0, and in next instruction R4 and R5 are subtracted and stored in R0. So sometimes both of them are written simultaneously in the sequential instructions. So here write after write instruction data hazard, we can see there's a possibility because we are using it in sequential instructions. Yeah, that's it. Do you have any doubts, or was I clear or not? Yeah, consider a direct map cache of size 16 KB with block. Did you understand the block offset which I explained, or is it still confusing? Okay, we'll do this question if you let me know if you have any doubts. So consider a direct map cache of 16 KB with block size 256 bytes. The size of the main memory is 128 KB. Find the number of bits in tag. So find the number of to find the number of bits in tag, we technically have to do we have to technically find everything, and then because there is no hard and fast rule for finding the number of bits in tag, so you have to find all other. For example, in direct mapping, this is the format. The address is stored in this format. That is the tag, the line number, and the offset. So to find tag, you need the line number and the offset. Offset, as I told, is determined by this 256 bytes because that is the block size. So 256 is by 256 bytes, and the total memory is 128 KB. 128 is nothing but 2 power 7 into K is 2 power 10. So total available address bits are 2 to the power 17. So 17 bits are available for you. In this, you have to find the number of bits which tag occupies, and the number of bits which the line number occupies, and the number of bits for the block or the line offset occupies. So line offset, as I said, 256 bytes. So line offset is 2 to the power 8, right? So yeah, 8 bits has gone to line offset. Okay, and then the line number is calculated by the cache size divided by the line size. Line size is the 256 bytes. Line size and block size can be, block size, frame size, line size. Everything is like, and we divide the total memory into blocks. That is what is all these blocks, frame, anything. Like it's all, one and the same. Anything you can equate it to the size of the block. Okay, so here, so 8 bits has gone for the offset, as I told. Next, line number on the cache size divided by the line size. Line size is 256 bytes, 2 power 8. Cache size on the it is given as 16 KB. So 2 power 4 into 10, 2 power 14, 2 power 14 divided by 2 power 8, 2 power 6. Adanale 6 bits has gone to line. So 6 plus 8, 14 has gone for this. So tag will be 3 bits. This is how you do for direct mapping. See, all 3 mappings on the calculations will be mostly same, but the one thing you have to remember is how the address for each mapping is represented. For direct mapping, now you have a tag, line number, and block or line offset. Okay, when you consider fully associative, there's only tag and offset. So this structure is what you have to remember. But as such, calculations will be very similar. Next, yeah. Do you have any doubts in direct mapping, or can we move to fully associative? So shall I move to fully associative?
இல்லண்ணா.
ஆனா இது மாதிரி அட்ரஸ் பிட்ஸ் கேஷ் இதெல்லாம் வச்சு சொல்லி தந்தாரா? மேப்பிங் சொல்லி தந்தார்ல?
மேப்பிங் தியரி லைக் சொல்லி தந்தாரு. அந்த 3 டைப் சொல்லி கொடுத்துட்டு லைக் இதுல வந்து பிளாக் செப்பரேட் பண்ணுவோம், அதுக்கப்புறம் செட் அசோசியேட்டிவ்னா பிளாக்ஸுக்குள்ள டைரக்ட் மேப்பிங் பண்ணுவோம், அதெல்லாம் சொன்னாரு. ஆனா இந்த மாதிரி நியூமரிக்கல்ஸ்லாம் கவர் பண்ணுவோம்.
Yeah, you can expect. ஏன்னா எங்களுக்கும் அதுதான் சொன்னாரு, பட் இதெல்லாம் it was asked. Yeah, அந்த yeah. So, do you have any doubts in direct mapping, or shall I proceed with fully associative? Typically, it's the same in all. Okay, you have to calculate the total memory on the available. Then you have to find the number of. You have to find the offset. These two are same. Like ella mapping, you have to find the offset and the main memory, then the total available bits. Then you have to find the offset. Then the line size in both direct mapping and set associative line size you have to find, or in associative also it is not used in the address, but you can always find the line size, because anyways you have cache size and the line size given in the question. Then only you can find the offset and all. So anyways you have this, but in only while representing the address you don't need the line size. So it's all the same. I'll do one in fully associative. Yeah, so in fully associative, same size, cache of 16 KB, block size 256 bytes, main memory is 128 KB. 128 is 2 to the power 7, and K வந்து 2 power 10. So 17 bits available. Similarly, அதுக்கப்புறம் 256 is 2 power 8. So offset 8 bits has gone. அதுக்கப்புறம் rest of the 9 bits are the tag bits or the block number. That's all. Here, yeah, this is typically the calculation. Yeah, as I said, even though you don't use the line number here to, in the address structure as such, you can always calculate cache size divided by line size. So 16 KB 2 to the power 14 by 8, same, they 2 to the power 6 lines you'll get. Next is set associative. Set associative, we generally divide the sets into the given specific number, and then inside that the main memory can be mapped anywhere, right? That is typically set associative. Here, same calculation, but just you'll find the number of sets which we'll do again. We'll do the calculation. So here we say consider a two-way set associative mapped cache with 16 KB with block size 256 bytes. The size of main memory is 128 KB. So same adhe mari you'll get 128 KB 2 to the power 17 bits. அதுக்கப்புறம் this one this one is 256 bytes, so 2 power 8 bits have gone there. So rest you have to, the structure is tag, set number, and the offset 8 bits, total is 17 bits. So how to calculate the set number? Set number is same, like lines as such, lines calculate பண்ணிட்டு what we do, line size, cache size divided by line size, same thing you do 64 bytes and 64 2 to the power 14 bytes divided by 2 to the power 8 bytes, you get 2 to the power 6, which is typically 64. So 64 lines you have got. You have found the number of lines. Now you have to find the number of set, because here in the address structure we have to give the set number and not the line number. So to find the set number, they have given it is already a two-way set associative map. So we find the line number and divide it by the set size, which is 2 here in this question. So we have 32 sets. 32 sets is nothing but 2 to the power 5. So 5 bits occupy the set, are getting occupied by the set. So here, as we already found 8 bits as the offset, 5 bits as the set number, we subtract 8 plus 5, 8 plus 5, 13. 17 minus 13 is 4 bits for the tag. That's all. Yeah. Do you have any notes? Okay. ஆனா இதுல நியூமரிக்கல் இல்ல, இதுல வெறும் இது மட்டும் தான் இருக்கு, ஃபார்முலா மட்டும் தான் இருக்கு. ஓகே. என்ன சொன்ன கமலேஷ்? Okay. Cache performance la cache, yeah, you have cache hit and cache miss. I hope you all know what is cache hit and cache miss. Easy da. So cache hit is typically number of cache hits divided by cache hit by cache miss is hit ratio, and the 1 minus hit ratio is 1 minus miss ratio is hit ratio, and 1 minus hit ratio is miss ratio. So yeah, this formula sir would have taught on the average access time, hit time plus miss ratio into miss penalty. We'll see in the okay. So given a cache hit time of 3 cycles, a cache miss penalty of 50 cycles, and a hit rate of 0.8, calculate the average memory access time and determine the new average memory access time if the hit rate increases to 0.9. It's just on the in the formula you have to substitute the values. Hit time, C is the time to access the information, and plus one minus hit, which is technically the miss one, into the time taken to miss it. Aதாவது, see, the average memory access time is when, logically, if you think, when there is a cache hit, you directly go access when there is a cache hit, you directly go take your whatever the data required from the cache. So hit rate into cache. When you miss, you access the memory. So you multiply miss penalty into the miss rate. This is the logic behind the formula. So directly, if you substitute the given values in this, you're going to get the answer. There's nothing very complex in this question. Okay, in the ஆமா, அது வச்சு திரும்பி again same formula you have to apply and get the answer. New average new average memory access time.
ஓகே, இப்போ வந்து அதுல கேஷோட ஆக்சஸ் டைம் இருக்குல்ல, அது எப்படி நீங்க இதுல இருந்து கால்குலேட் பண்ணுவீங்க?
ஹிட் ரேட் தான் கொடுத்துட்டாங்களே. ஆமா, 50 cycles. Yeah. With size of 1 MB and each memory location storing 32 bits of data, how many address lines are needed to access the memory, and how many data lines are required, and what is the total memory capacity in bits? So இது வந்து நான் tell you how to do, and calculation வேணும்னா வந்து ChatGPT போட்டு வச்சிருக்கேன், அதை நான் காமிச்சிடுறேன். So here what you have to do is same, அதே memory total 1 MB. 1 MB is nothing but 2 to the power 20. So 2 to the power 20 na total address bits you have 20. So 20, yeah, you have 20 bits available. Adula how many address lines in the way mapping alla. So you just need how many address lines and how many data lines. So data lines namakanga 32 bits of data are given. So 2 to the power 5, 5 is 5 data lines. Then address lines vandu, wait a second, one minute guys, I'll show you the calculations. Yeah, this one. I'll explain it from here. Yeah, 1 MB na 2 to the power 20 bytes. Adala you have so each 32 bits in we have given, but here it's in bytes. So 32 bits, when we convert it to bytes, it's 4 bytes, because 8 bits make a byte, right? Adanala 32 divided by 8, you get 4. So 4 vandu 2 to the power 2, 2 to the power 18, we get these are the address lines, like the total address lines available. Next, data lines. Data lines உங்களுக்கு வந்து 32 bits nala you directly you get 32, you need 32 data lines. ஏன்னா வந்து 32 bits நம்ம ஸ்டோர் பண்ணோம். ஜெனரலி இப்போ வந்து what we generally do, இப்போ 16 KB நம்ம we saw in the earlier question, right? 16 KB we take 2 to the power 10 into 2 to the power 4, so 14 bits we need to store. So when we need to store 32 bits, you need 32 data lines, right? Another 32 data lines. And similarly, address lines, as I explained, to 20 bytes. This remember to calculate the bits, calculate bytes from the number of bits given. Then you divide them, and that is the number of address lines required. Total memory capacity is 1 MB into total memory capacity வந்து they have asked in bytes அதே மாதிரி in bytesல they have given. When you have to calculate in bits, you have to multiply into 8, because as I said, 1 byte is 8 bits. So that is why 8 becomes 2 to the power 3, and we are getting 2 to the power 23 bits.